So first of all, hi everyone and welcome. I am speaking to you from Virgo, which is, as you may know, a gravitational wave detector that is located in Cascina, which is near Pisa in Italy. And today we will do a tour of these interferometers. So there are only three of them working at the moment in the world, and only one of them is in Europe. The other two are the LIGO detectors, which are in the US. So this is a very special and unique place, and you will get the chance to see a lot of it. But before we do that, of course, we have to start from the basics. So what do we do here? What are gravitational waves? Before I start, I want to tell you that if you have any questions, if anything I say is unclear, or if you want some additional information, you can write it in the chat, and then I will Federica will read them to me, and I will respond. So let's start from the very basics. What are gravitational waves, and what is the point of what we do here? So first of all, gravitational waves are ripples in space and time. So there is a fabric of space-time that permeates all of the universe, everything around us. We live in the fabric of space-time, even though we don't realize it. And this fabric is not static. It's not something that can't move, can't be changed, can't be perturbed. It can be perturbed. And this was something that was theorized by Einstein, by Albert Einstein in his theory of general relativity. That when we have massive bodies moving in space, orbiting around each other, or just one body, but it must be asymmetric, if these massive bodies move one around the other and orbit one around the other, they perturb space-time. They create waves that are exactly like the waves in a pond. Like if you throw a rock in a pond and all the waves are created in the water, it's exactly the same thing. But these waves are not propagating through water. They're not propagating through air. They're propagating to space, through space-time. And so that means that they affect everything around us. They affect us. They affect every object around us. They affect air. And we will see how they affect all these things. But first of all, I want to show you a practical demonstration of this. So we say the fabric of space-time. Why do we say the fabric? Because it does behave like a fabric. So this is just a piece of fabric, a piece of elastic fabric. If I put a very heavy object on it, it warps. So you can see that it was flat before, and then I put a heavy object in it, and it warped. So masses curve space-time. So space-time, this is space-time, and it has been curved by the presence of this mass, which is the first point that Albert Einstein made. But the second point is that the curvature of space-time can affect the movement of masses, which is a bit more complicated, but I think it's pretty clear from this experiment, this physical piece of fabric. If I take another mass, this is a lighter mass, this is a rock, while this one is a ping pong ball, tabletop tennis ball, and I make it move through this space, you will see that its movement is affected by the warping. So it starts orbiting, and then, sorry, if I move it, it starts orbiting, and then it falls. It tends to fall toward the heavier object. So if I just put it here, it just falls there. If I give it a velocity, it starts orbiting, like planets orbiting around the sun. And after a while, it falls in the center. So this is what happens to objects in space-time. And what are gravitational waves? They are just ripples. They are movements. When I put this rock, when I put this mass in our fabric of space-time, we can see that it creates some ripple, it creates some movement. This is what gravitational waves are. But there is a big problem with these waves. Well, quite a few big problems in detecting them, which is why Albert Einstein himself didn't think it was possible. He didn't think that gravitational waves would be detected just about 100 years after he theorized them. Why is that? Because first of all, their effect is extremely small. It is extremely, extremely small. It's smaller than the diameter of a proton. It's 1,000 times smaller than the diameter of a proton. So that means that it's a very, very small effect to have to detect. But that would be a problem. But maybe not the biggest problem, actually, because we do work in particle physics, in nuclear physics. We work with particles that small. So there is an additional problem, which is the fact that gravitational waves affect everything. So if I have a ruler to measure the fact that, for example, when a gravitational wave passes through me, and this is something, sorry, that I have not said yet, what do? They warp space-time, meaning that they make things shrink and then dilate again. They make you a bit smaller and then a bit larger again every time they pass through you. Of course, this effect is minuscule, so they don't really do anything bad to people or to things. We don't notice them, but that's what they do. So if I had something that is a certain length and a gravitational wave passes through it, that length will get bigger and then smaller for a very, very brief amount of time, a fraction of a second. The problem is that if I have a ruler to measure this, maybe I have my piece of something that I want to see if a gravitational wave is passing through, for example, this piece of plastic. If I have a ruler to measure it, the idea could be, well, now this piece of plastic is a certain length. When the gravitational wave passes, it will diminish by a very small amount, but it will diminish. And so if I have something to measure, I can use that to measure it. But the problem is that also the object that I use to measure will be affected by the gravitational wave. So how can I do this? It seems to be a logic impossibility, basically. But it's not, because we actually do manage to do this through the use of light. Because light is not matter, so light is not affected by the passage of a gravitational wave. And so what we do is we use a principle called interferometry. Interferometry has not been invented to detect gravitational waves. It was already invented at the beginning of the past century to do some experiments with light. But it is very useful to detect gravitational waves, and I will show you through what I have in front of me, which is a model of an interferometer, because the object that we use to measure gravitational waves is called an interferometer, Virgo, which has 3 kilometer long arms, which is just outside of this building. Its arms are 3 kilometers long, so very, very long, is an interferometer at its very core. So it's exactly the same in principle as this small model that I have in front of me. So what does it do? How does this work? So as you may know, light is also a wave. It's a particle, but it's also a wave. And that means that it has the shape of a wave. It goes up and down and up and down. This is the up and down of energy. So the energy of the wave goes up and down and up and down. Each wave has this shape. If we have two waves, two of them, two waves of light, and so see now they are two, and they are in this phase, in opposing phases, they cancel each other, because the top of one will be the bottom of the other. So if one has energy +1, the other has energy -1, for example, and so they cancel each other, basically. But if they are in the same phase, so if their tops and their bottoms coincide, then they will enhance each other. So they will create double the light instead of no light. So like this, no light, like this, double the light. This is a very useful principle that we use with an interferometer. How does this work? So first of all, we have a laser source. It could be a source of any light, but we need a laser because it's very collimated. A laser, as you may have in mind, a laser pointer that you can use to point at slides in school, is a very collimated source of light. So we have this very collimated source of light that gets to a mirror that is here in the middle. And this mirror is called the beam splitter. It splits it in two. So it gets here, and then it gets split into beams. So one beam of light becomes two. One goes down this arm, and then at the end there is a mirror, and the other goes down the other arm, and at the end there is another mirror. Then they come back, right? And in those points in which the two arms, if the two arms have the same length, the two beams of light will cancel each other out, because they start when they get divided, they start in opposing phases. So as we were saying here, they start like this, they come back like this, and they cancel each other out. If, and this is very important, the two paths are the same length. So you get light out of this interferometer, and you get what we call a dark fringe. So we get fringes of light, because of course the beam has a certain dimension. So there will be points in which they cancel each other, and there will be points in which they enhance each other. But the center will be dark with what we call dark fringe. But this only happens if they do the same path, because again, if they, from the beam splitter, they get divided in opposing phases, they only stay in opposing phases if they travel the same distance. If they don't travel the same distance, they get a bit overlapped. So they're no longer in opposing phases, and so we see some light. You can actually see this at the end of this very small interferometer. I hope you can see it. You can see that there are some fringes. There are some areas that are dark and some areas that have light. These are called fringes of interference, and they come from, again, the interference of these two beams. The points in which you see darkness, wait, let's try to maybe not touch the, exactly, so, and now I will tell you why they move so much, but the points in which you see darkness are the points in which the beams are canceling each other. And the points in which you see more light are the points in which they are enhancing each other. What happens when a gravitational wave passes? Since a gravitational wave moves in the same, in a circular pattern, it moves from the center circularly, it will affect the two arms in a different way, because the arms are at 90 degrees. So from the perspective of the center of the gravitational wave, they will be affected differently. One will be stretched in a different moment than the other. So maybe one stretches and the other doesn't, and then a second later the other stretches and the first doesn't. This creates, for a split second, a difference in the two lengths of the arms. And this difference means that the interference pattern changes and we see light. We are no longer in dark fringe, but we see some light, because from the perfect opposing phases, we get some moments of light. This is how gravitational waves are detected. And this, in principle, may seem quite simple. Even this interferometer then could do it. But why is it so hard to detect them? Why did it take 100 years? And why did Einstein think that it would never be done? Again, it's because what we are trying to measure is extremely small. Remember, smaller than the diameter of a proton. So it's extremely small, and there are a lot of disturbances around us that may mimic the effect of a gravitational wave, because they change slightly the length of these arms. Basically, these arms are made, the distance, what counts is the distance between these mirrors, between the central mirror, the end mirror, and the end mirror. So these are the distances that must stay the same to a degree of less than the diameter of a proton. So they must be extremely still. And now we will see how we keep them extremely still. But there are many things that can disturb these mirrors, make them move, and therefore change the distance between them, and so change the path, the length of the path of the light. You were seeing before, as we were showing you this light path, that it was moving. you will see that now it's pretty still. But if I tap on the table, you can see that it moves, right? That it gets disturbed, it starts looking wonky. Because I'm creating a noise, I'm creating a vibration that is doing exactly that. It's moving those mirrors a bit, so it's changing the length of the arms. This also happens to Virgo. So Virgo also has this problem, Virgo and LIGO and all gravitational wave detectors. And these noises are what makes gravitational wave detection so hard and why it took so long to do it. So what are these noises in practice? What are the biggest disturbances? So the first one is maybe intuitive from what I just did. I made the table vibrate. I put some vibrations on that table. What is the equivalent of that in nature? It's earthquakes. It's seismic noise. So the earth is not still. The earth moves all the time, vibrates all the time. And seismic movements of big and small affect, of course, the mirrors of Virgo. If the mirrors were just standing on a table on the ground, it would be impossible to detect gravitational waves because the movements due to seismic noise would be far too big. And now we will see how we can make the mirrors move less than just if they were sitting on this table. But seismic noise is not the only noise. Also, well, or better, seismic noise, the vibrations of the earth are the main noise, but they can come from various sources, not just earthquakes or seismic activities in the most classical sense, but you can also think of thunderstorms. So if it rains a lot, if there is a lot of wind, the wind makes all the buildings of Virgo vibrate, and that makes the earth vibrate, and that makes the mirrors vibrate. We are close to the sea, to the Mediterranean Sea, and waves that impact on the shoreline of the Mediterranean Sea also make the earth vibrate, and they disturb Virgo. Actually, waves from the sea are one of the biggest disturbances. But then we also have electromagnetic noises. We have noises from all man-made activities. So there is, when we are data taking, there is a no-fly zone on top of Virgo because the vibration from planes would disturb the functioning of the interferometer. So would, for example, nearby there are some wind turbines to create electricity. And those had to be studied and had to be taken into account to subtract them from the signal of Virgo, because everything, all human activities that create vibrations in the ground can disturb the functioning of the interferometer. So how do we protect these mirrors from vibrating so much? We use these things. This is actually a prototype. So it's not exactly what they look like right now, but it's pretty similar to what they look like right now, of what we call a super attenuator. So what it does is in the name. It attenuates a lot, and I will tell you by how much. It attenuates quite a lot the vibrations of the ground. So let me show you how this works. So here you would have the mirror, and the mirror is attached to here, and this would not be there. This is just for safety reasons, but the mirror would be just suspended from all these super attenuators. And then you have a chain of all these stages. There are 7 of them. And this chain is attached to the top. So again, these are also here for safety, but they wouldn't be there. So it would be just a mirror attached to this chain of 7 pendula. And it's important that they are pendula, attached to the top. And then the top is attached to the structure and goes down deep in the ground. So that means that the movement of the mirror is dependent on the movement of these 7 pendula. But why pendula? Why do we use pendula? Because in physics, pendula have this very interesting property that if you attach something to a pendula, let me show you. Ah, yes, true. I have them here. So this is a pendula, right? A pendula just means something, a mass attached to a cord to a point here at the top. So if I move at a certain frequency, basically what's at the bottom doesn't move at all. So if I move very quickly, you can see the top is moving a lot, but the bottom is not moving at all. So you can see that the top is basically standing still while the top is moving a lot while the bottom is standing still. If I move slowly, then the bottom also moves. But if I find that frequency for which I can move the top by a lot and the bottom will stay still, you can understand that I can attenuate a lot of vibrations. So imagine that the Earth is vibrating because there is an earthquake. The vibration goes up to the top, and the top starts vibrating, but it is attached to a pendula. So this first stage will vibrate much less. And they also have this interesting property that if you attach more than one of them, one to the other, so if you attach, as there are 7 of them, the vibration will be attenuated even more. So using this principle, we are able to attenuate seismic noises, seismic movements of all kinds. So coming from the earth, coming from thunderstorms, from the waves, etc., by a factor 10 at the 12th. So if, for example, the ground moves by 1 millimeter, the movement of the mirrors is 1 millimeter divided by 1 followed by 12 zeros. So it's attenuated a lot. That allows us to keep the mirrors still as we need them to detect gravitational waves, because again, they need to be, that distance must not change by a factor smaller than a proton. So they have to be very, very still. And anyway, even if we have these systems in place, if a big earthquake hits around here, of course, that will disrupt the functioning of the detector. And one last thing that I want to show you in here, so start thinking of if you have any questions before we move to the next stage, is a real mirror of Virgo. This is what is actually attached at the bottom of those superattenuators. This is a real mirror, and perhaps some of you will be thinking that I am making fun of you, that I'm joking with you, because you look at it and it doesn't look like a mirror, right? It looks transparent. It doesn't look like you can hang it up in a bathroom and you can put makeup on looking at it, because it's transparent. As you can see my hand behind it. Why is it transparent? Because we don't use visible light. We use infrared light, which is just another wavelength. As you know, light is a spectrum, and humans can only see a small part of the spectrum. But there are other parts of light that we can see, radio, ultraviolet, etc. And one of them is infrared. So we use infrared light. And for infrared light, this mirror is a mirror like the best mirror you've ever seen. If you could see in infrared, you could take the best selfie in the world in this mirror, but you can't. So this doesn't look like a mirror to you. It looks like a piece of glass. But there are other interesting aspects of this mirror here. I hope you can see this, and perhaps Federica will have to zoom a bit to make you see them. Each side of the mirror is attached to 4 strings. 2 of them look a bit more dark, and 2 of them look almost transparent. I hope you can see them well. They do look transparent. Why? Because as you see around this mirror, there is a ring of metal, And that ring of metal is held up by metal strings, while the mirror itself, actually the mirror itself doesn't touch that ring. And I will tell you why that ring is there in a minute. But the mirror itself is not touching that ring. It is held up by glass wires. So they are wires made of the exact same material of the mirror, which is glass. And they are extremely strong. And it's important to have glass wires because, as opposed to metal wires, they don't create interference, magnetic interference with the mirror. And the fact that they are glass wires, it looks like it's very hard. It's very hard to suspend something that weighs more than 40 kilos. So this mirror weighs more than 40 kilos, and it is hung up by 4 glass wires. And that sounds very complex, and it is as complex as it sounds. It is a very hard technological challenge that gravitational wave detectors such as Virgo and LIGO have had to face in order to function. But what does this ring do if it doesn't touch the mirror? So why is the mirror encapsulated in this ring? It's to control it, because as we said, the mirror has to stay still. It can be touched. It can be in contact with the ground, because if it's in contact with the ground, then why did we append it to a series of pendula? It has to. The only point of contact has to be. We have had a problem with our stabilizer. Wait, let's see if we can fix it. Let's try to turn it off and on again. It's not stabilizing. Okay, it's back. Sorry for that. But sometimes we will have to move this mirror, right? So how do we do that? We can't touch it, because if we touch it, we will introduce vibrations, and all of the super attenuator we have done will have no point. So the way we do it is that maybe you can see that on the bottom of the mirror, on the back, you can see 4 small imprecisions. Let's call them 4 small points that are at the back. Maybe if we zoom in, we can see them. Yeah, exactly. You can see them now at the top of the image. There is one of them. Each of them, there are 4. Each of them is a magnet. And this entire metal ring is only to hold up these 4 magnets that you can see here in the back. There are 4 circuits. And if you make a current pass through a circuit, of course, it creates a magnetic field. And since the mirror has magnets embedded inside it, it can be controlled through this magnetic field. So in this way, we can control the movement of the mirror a little bit and with a lot of precision, so it doesn't get disturbed. So this is what I wanted to show you in this room. And before we move to the next part of the tour, I want to ask you if you have any questions. You can write them in the chat. I will give you a second to write your questions in the chat. Meanwhile, I will tell you that we will lose connection for a moment as we move to the tunnel, which is our next step. So if don't worry that we will disappear for a minute or so. We will come back, and this will also happen as we move to our next steps, because between each step we will lose connection for a few minutes. Before we do that, no questions? Federica? Meanwhile, as we move, while we move, if any questions come to mind, either because something I said was unclear or because you're curious about something else, you can write them in the chat and we will read them as we get to the tunnel. So let's move. We'll be back in a couple of minutes.